So we have an object that eventually falls towards the surface of the earth based on the effects of gravity, and we're given 2 points. We're told at t equals 0, the ball is dropped off a 550-foot building. So let's write that down. We have 0 as the input, 550 is the output. 3 seconds after it's dropped, so the input is 3 and the output is 405.1. The height of the ball can be modeled by the following function where we have a and b, which we need to create, and t is the number of seconds since it's been dropped. H of t is the height above the ground, the ball is above ground. So use the data to write 2 equations. Well, it already gives me a general equation. So this is real quick, this is your t and this is your h of t. So I'm going to write my equations off to the side here. Here's one equation. H of t, okay, what is my h of t? Let me just put this down first so we can model it. H of t is 550. A plus b, okay, my input is 0 squared. Well, 0 squared is 0, and 0 times b is still 0. So this is 550 equals a plus 0, which is just 550 equals a. That's one equation. Okay, let's look at the second equation. So let's go with the second one. My output is 405.1. But then we have a plus b, and my input is 3 squared. So this is my second equation. I could leave it like this, or if I wanted to, I could go ahead and write 9b. 3 squared, 9b, all shows that you can write 2 equations. Okay, so I've got that done for part A. Part B says solve for these. Well, I've already shown that I solved for one of them. This is me solving for A. Now it's really easy to solve for B because I know that A is 550. So 405.1 equals 550 plus 9 times B. I'm going to grab a calculator here because this is the calculator portion. I'm going to show my work here, subtracting 550. So 405.1 subtract 550. That's negative 144.9 equals 9b. Divided by 9. I'm not going to stress about that using the calculator. So negative 16.1 is the b value. So we've gone through 2 of the. Please underline right now where it says rate of change. Average rate of change. So average rate of change is your change of y divided by your change of x. So it's what you learn, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And it specifically tells me that we want to find the average rate of change from 0 to 3. So there's my 0, and here's my 3. And I already know that 0 corresponds to a height of 550 above the ground. 3 corresponds to 405.1. But it also says show your computations. So I'm still going to use a calculator because I'm going to be a little bit lazy, but I need to show that I know how to do this. So this is x sub 1, y sub 1, x sub 2, y sub 2. So 405.1, there's your y sub 2, subtract 550 over 3, subtract 0. And then I'm doing the rest in a calculator. I've shown that I know how to set it up. 405.1, subtract 550, and I'm going to divide that by 3, subtract 0, and I end up with negative 48.3. Now here's the big deal. I would say that 40 to 50% of kids were able to get this, and then they got part of it wrong. Here's the reason why. When we're talking about average rate of change of the ball, we have to do it in terms of, this particular problem is feet per second. Feet per second, and that has to be added to it. The average rate of change when it's within the context of a problem has to have the units at the end. Okay, part B, again, a lot of students put this down, and then even some students who probably have had physics put down feet per second. But where is this being calculated? It's not just like any random area. Underneath what parameters? It tells us at the very beginning of that problem. From what to what? From 0 seconds to 3 seconds. And that would be our part 2 of B. Okay, so now we're going to go ahead and it says consider the average rates of change. We're going to go from 3 to 3 to, and then here we can see we're going to go from 3 to 5. So we're going to calculate the average rate of change, and then we're going to compare it to the other one. So when we think of this, okay, here we go. We're at the top of the building, right? Does everybody agree with that? And this object is going to be going all the way down until it hits the ground. And so we already calculated from 0 to 3 seconds. And we said this average rate of change from 0 to 3 was, the ball was dropping 48.3 feet per second. So now we're going to go from 3 seconds to 5 seconds, and we're going to calculate that average rate of change. By the way, look at that picture right now. Not that I'm a great jogger. Do you think that the average rate of change is going to decrease at a faster rate based on my picture, or do you think it's going to be the same? Is it linear? It's going to decrease at a faster rate. Okay, so how are we going to do this? Exact same way. We're going to go between 3 and between 5. So we'll have, those will be our endpoints, but we're calculating the average rate of change between them. We know 3 already goes to 405.1. A couple different ways we can figure out 5, but here's one way. Let's come up here to this equation. Let's go second plus 7, 1, 2 and clear everything out. And let's go to y equals. And now I'm going to go to my equation. Well, what is the equation? Here's the equation. My A was 550. So I'm going to type in 550 plus the B is negative 16.1. Negative 16.1. And there's no t, it's the same as x squared. There we go. Okay, let's go up to the windows. Let's adjust this. We know that we need to see to the top of the building, so let's go up to at least like 570. And let's see what this looks like. So this represents the ball is being dropped from the top of a building, 550, and eventually it's going to hit the ground. All right, you ready? What's the only ordered pair that I'm missing? I'm only missing the output value for what input value? 5. So we'll go second, trace value, and type in 5. 5 goes to 147.5. Now if it says we need to show our calculations, how do we do that? Anyone? How do you find the average rate of change? y2 minus y1 over x2 minus x1. So I would be safe personally. I would show my work and then I'm going to use the calculator to do the hard stuff. 405.1 over 5 minus 3. So I'm coming back here and going 147.5 subtract 405.1, and then I'm dividing that by 5 minus 3, and here is my answer. Did I type in something wrong? Can you guys see if you agree with me, please? I thought that may look a little different from this morning. Can you check with me really quick to see if you agree with that? I got the same thing. I got the same thing. So it is falling or decreasing at a faster rate. So between, not including 3, between 3 and 5 seconds, it is falling at a faster rate. That makes sense because quadratics are not linear, okay? So it's falling at a faster rate. We can kind of see that if we're just making a prediction. Let's go on to the very last one. It says, for this model, based on this information, how many seconds is the model appropriate? So basically, what they're asking is, what should be the domain of this function? When should it start? Like, should we consider the ball coming up to the building? No, when does it start for the x values or t values from this problem? It starts at 0. So it starts at 0. And then when does it end? Where on the graph do we end this? It's coming right here, correct? Do you guys agree? Do you agree it ends right here because we know the ball doesn't go into the ground? So I need to find this 0. So go second trace in your calculator. Second trace 0. I know it's between, we're just going to say 3 to 6, somewhere in there. And let's get an exact amount. So 5.844, something like that. So the appropriate model for this function will go between 0 to 5.844. Why? That's when the ball hits the ground. We know the ball is not going to go beneath the ground.